All right, let's continue on with talking about interactive views in visualization, analysis, and design. So in the previous segment, we were focused on these strategies for handling complexity by manipulating a single view interactively. Now let's move on to this question of faceting into multiple views. So what are the considerations involved with multiple views? Well, it's about juxtaposing two views side by side, partitioning into views, and superimposing two layers on top of each other. Let's start with juxtaposing. So the issues involved in juxtaposing and coordinating views, first of all, is what are the visual encoding of these views? Are they the same or are they different? How do we link them up with things like highlighting and navigation? Which aspects of the data are shared between the views? Is all the data the same? Is there a subset in one versus another? Is it completely partitioned, so none of it's the same? And not just do we have linked highlighting, but do we share the navigation? So a really fundamental idiom for interaction is this idea of having linked highlighting between views. It's often one of the places you start. If you have two separate static views and you thought, how would I usefully add some sort of interactivity to them if I could see two of them side by side, you'd have linked highlighting where when you select some number of items in a contiguous region in one view, you're interested in seeing what happens in the other view if the analogous marks corresponding to those items are also highlighted in that other view. It's a really powerful and flexible and quite pervasive idiom for interaction. So understanding the relationship between the views through this idea of linked highlighting. In this particular example of the EDV system, it's looking at baseball statistics of players in baseball teams. And so the first thing we notice is we have the views look different. We have different visual encodings. Let's call that the multiform approach, where the views are not all identically visually encoded. So what's happening with the data is it's shared in the sense that all of the items of data, in this case, baseball players, are shared between the two views. What's different is that different attributes are shown across those different views. In fact, that's what makes them different visual encodings. So we see we've got, a bar chart of the years. We've got a distribution plot of the log of the salary, some scatter plots, again, another bar chart. And the key thing that's going on here is what was selected in the top right view is high salary players. And then we see the distribution of the high salary folks on these other views. For example, we can see on the top left, they're scattered across all the years. So it's not just based on seniority. We can see in the bottom, they're scattered across all the positions. So it's not just the pitchers or just the first basemen. And then what we see in these scatter plots, the one on the left of assists versus putouts, again, they're spread. But in that middle right scatter plot, the one of hits per year, we see that the high scoring people are also the heavy hitters. So that's something that could make sense here. Also notice a few nuances. For example, what we see is that we have this particular way of interaction where as we select something in one view, these bar charts, for example, we're showing only a subset of which percentage of the bar. So it's acting a bit like a stacked bar chart here. So this kind of ability to highlight subsets is something you need in things like bar charts as opposed to something like scatter plots. Sometimes linked highlighting is called brushing and linking. These are just synonyms. Now, when you're linking views, one thing to consider is the directionality. In general, unidirectional linking, where clicking in one view causes a change in the other, but not vice versa, is typically, might be easier to program, but it's usually less useful to the user than bidirectional linking. So let's just look at an example of bidirectional linking. Here we see that when we move the mouse in one view, we're seeing the effect on the other, this radial view, and vice versa. Now, when I move the mouse in the radial view, I see the connection to the distance in this view. So this is a nice example from Peter Bashai, along with an article that explains exactly how this was coded up to be scalable. All right, what's another idiom? The idea of overview detail. This is another major idea. Here's a particular system, an older version of Google Maps, when it did have these overview detail views. The encoding could either be the same across both views or different. In this case, it's the same. We have a bird's eye map in the lower right, and then this larger detail view. And in terms of the data, well, there's a subset of the data in one view compared to the other. In this geographic map, it really is just that the camera is zoomed way out. So we have a viewpoint difference. And importantly, the navigation is shared here. If you move in the main view, you see that little box representing your location move. And likewise, you could drag that little box and that would then change the main view. So overview detail is not necessarily the same representation. Here's another example where the encoding is the same. What is crucial about overview detail views is that a subset of that data is shared. So let's take a look at a unidirectional navigation. And in some cases, unidirectional exactly makes sense with overview detail. So let's look at the example of this from Jeff Hare's curriculum on the observable site. And here's an example of a linked view. So we've got this global overview at the bottom showing all the time, and we can simply move this around. We can make it larger, we can make it smaller. The point being that we're really driving the detail view on the top with the overview on the bottom. And also, while we're in this notebook, let's take a quick look. There's another good example of something where we are selecting in one view where's the one I'm looking for? Here we go, where we're selecting in one view. And notice how that's changing what we see in the other view. So this is an example, another example of a linked view where actions in one view changes the interactive highlight selection in the other view. Okay. Let's get this one out of the way for 1 minute. So what's another idiom we could have? Well, this idea of a very particular kind of a detail view, a very small pop-up, often called a tooltip, where it can either appear on hover or on click, and it gives you more detail on demand. Now, one thing to be aware of, although these can show additional information in a useful way, information that you're choosing not to directly visually encode, keep in mind that you're not going to be able to get an overview from these tooltips. You would have to remember what the tooltip saw before. So if you ever need to provide summaries or gist or overviews, you are not going to get that from a tooltip. So always think about the trade-off between visually encoding information directly in the view and something that truly is extra that you don't need to understand overviews. That is what a tooltip is for. Another data journalist quote from Gregor Reich: if you make a rollover or a tooltip, assume nobody will see it. If it's important, make it explicit. That is a useful concept. So just to give an example of what this sort of dynamic tooltip can do, right? Notice how this is extra information, which you could assume in some sense it's a way to read off what might have been maybe a little bit too difficult to read because we're zoomed way out, so getting that exact date. But notice how we're still able to see the date from the visual encoding. So essentially a tooltip that's expanding on information that you already see visually is often safer than one that's giving completely new and different information. All right, what about small multiples? So small multiples is another one of our idioms. And the idea is that we're definitely using identical visual encodings. Here's an example with line charts of company stocks. And the key idea is that the data is not shared between the view. It's different slices of a data set, right? And it could either be sliced by item or sliced by attribute. In this case, we're seeing stock prices for different companies. And so the key part about small multiple views is it is, as the name suggests, a number of small views. And then often we have some sort of interaction between them that can help. For example, in an interactive small multiple view, you would often have linked highlighting so that when the mouse is over something in one view, you see the analogous spot in the other view. Here's an example of questions on metafilter, and by moving the mouse, we actually then see what we have in each one of them. I'll show an example of that in just a sec. So here is a video of a nice system called buckets, where we're seeing a lot of these at the same time. We're seeing multi-directional linked highlighting. Notice how as we move the mouse, we're actually seeing, let's run that again. As we move the mouse, we see that spot highlight across the different views. We see, in fact, this was the prototype of that radial versus rectilinear linking. We see examples of tooltips coming up. So this, and of course, it's a multi-form view because we have different visual representations, not just line charts, but also this shot graph and a number of other widgets and controls. So let's think about the trade-offs here. With juxtaposing a view, what are the costs? What are the benefits? The costs are display area. Remember, pixels are precious. We have very few. Every time we add another view, we take away the number of pixels available for the other views. So, you know, if you've got two views side by side, each of them could perhaps only have half the area if they are of equal size. So the benefits is that you've got a really different cognitive load. Think about the slogan of eyes versus memory. It is much lower cognitive load to move eyes between two views than it is to have a single changing view, remember what that view looked like before, and compare what you see in front of your eyes now to your memory of previous states. So with juxtaposing, you don't have that cognitive load, but of course, there's a real limit as to how many views you can have side by side before you run out of pixels. So let's think about an example of this. Here, I'm seeing actually not that many data points and not that many frames, but it's really hard to follow this animation. This is a single changing view. And if I sort of focus on one of these, okay, yellow, 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 orange, yellow, yellow. All right, I've tracked what happened to one of these, but there's change happening all over this screen. And so it's very hard to attend to get a gist of what's happening because change is happening in a scattered way over many frames. So this is in contrast to that really easy case, that special case of animated transitions where there is a sort of uniformity to the movement. When things are happening in a scattered way, it's actually quite hard to follow the animation. Here's actually exactly that same data shown with small multiples. If you remember back to my very intro segment, this is actually that same data, but we are much more able to move our eyes in between the small multiples to notice, aha, this time step here is the one where we see an overall the gist that's different, as opposed to just seeing these one by one. So we really only had 8 frames and, you know, under 30 dots, and it was still hard to follow. So, and this particular data set was looking at gene expression levels. But this is just one example of some of the strengths and weaknesses of juxtaposing and animation. Animation can be particularly useful if you're just flipping between two views, 2 frames. For these sort of, that's actually how they discovered Pluto, was a blink comparator of comparing 2 frames and noticing when something jumped. So it was a planet, not a star, or at least a dwarf planet. Okay, so now that we've seen a set of these possibilities, let's understand the design choices with view coordination. We can have the same or different visual encoding. We can have all or a subset or none of the data. And there's really 4 boxes here that are interesting. If the encoding's identical and the data's identical, well, we don't need multiple views. It's completely redundant. And if the encoding's different and none of the data's shared, they're not linked in any way. So it's really the idea that we could either have same data and different encodings, or same encoding and different data, or these cases where we've got the subsets. Overview detail views can either change the encoding between the views or be the same between the views. So here's another example of a fairly aggressive multiple view system. And it's worth noting that, you know, there's a lot going on here. There's scatter plots, there's parallel coordinates, there's a large detail scatter plot. We see a bivariate color map. We see geographic views. We see an overview detail up in the corners of bird's eye view, and then there's a detail view near the middle. But I want you to notice one thing, which is we've got some things that are just lists. Now, by themselves, we often don't necessarily find a list all that useful. But if you need to support lookup, particularly across a complex multi-view system, it can be very useful to be able to get at a particular attribute in order to say, have those alphabetically listed so you can get them, because the linked highlighting allows you to see where they fall in those other views. So in some cases, you can think of these as more supplemental views, but they definitely can serve a purpose in these multi-view systems. Now, this might lead you to ask, wow, how many views is okay? That's a complicated question. There's not a single right answer. This particular system is probably pushing some of the limits of what might be feasible. So it's a very, very context-dependent question about the expertise of your target users and how long they plan to learn the system versus use the system, and whether they're doing deep analysis or just something simple. So it's not trivial to answer, but it is something to consider, because even keeping track of what's happening between those views and learning how they're linked can have a time cost. So let's now talk about partitioning. How do we decide how to chop up the data between the views? What are the design considerations for that? Well, when we're thinking about partitioning, there's this fundamental question: how do we divide the data? And typically, you are splitting into regions, right? We can think of views as regions, and we're splitting into these regions according to the attribute, because we're usually doing this with some sort of multi-attribute data set, not just, if we had only a single attribute, we probably wouldn't need multiple views. So typically we're doing this when there's some complexities to the data. So when we divide into views, spatial regions, what we're doing is we are using a spatial proximity to signal what's important. You're encoding the association between the items according to what is in which view. And that means that the order of doing these split into regions has really major implications for what is visible to our perceptual systems. So let's look at an example. Let's say we've got a multi-attribute data set. In this case, we're thinking one of the attributes is states, one of the attributes is demographics. So how might we look at that? Well, one thing we could do is we could say, okay, we're just going to have a single chart. It's going to be a grouped bar chart. And so let's analyze what's happening here. First, we take our table and we split by state. And then there is one region for each state. In this case, we're just looking at 6 of the states. And then within each region, instead of just having a single bar, we're actually having a complex glyph, because we're showing a grouped bar where every one of those demographic regions is shown as a bar here. So what's easy and what's hard? What's easy is to compare within a state. We immediately notice, oh, we've got a roughly similar pattern across each state, so we don't have wild demographic shifts, although we do have some nuances. For example, a lot of certain younger people in California compared to a place like New York. So it's easy to compare within a state. It's a little harder to compare across ages. If we want to compare the demographic of 18 to 24-year-olds, we have to attend to first one bar here and then jump over to another bar, jump to another. And there are many things in between that serve as distractors. So that is a harder perceptual comparison. We can take that same data set and split it differently. We could first split according to these demographic groups, and then for each demographic group, we could have a bar chart, which is what we've got on the right. Okay, now what's easy? It's really easy to compare within age. Now, if I go back to that 18 to 24-year-old group, which is that fourth one down, oh, I see. It's actually steadily decreasing as we go from California down to Pennsylvania. Harder to compare across states. That kind of comparison we made of what is happening within California, it is not as easy. Let's get a little more exotic. Let's think about an interesting data set, which is real estate in London. So first, we're going to split by the neighborhood attribute. Then we're going to split by, and so that's these large boxes, Harrow and Enfield and Bromley. Now we're going to split by the housing type. So flats like apartments or terraces or semi-detached housing or fully detached houses sitting, not touching any other house. Then we're going to partition by time. So here within each of those little blocks, we've got the years or the rows and the months or the columns. And now we're color coding by the price of the real estate. So what can you see here? Well, you're very able to understand neighborhood level patterns. What's expensive? That stuff in the middle of the city, as opposed to the ones further out that are cheaper. You can also really easily see when is there a huge disparity between detached houses, which are in the lower right of each block, versus the others. And we can see there's some places where, for example, here, we really see these strong disparities, whereas in others, we don't see nearly as much disparity. So that's the kind of pattern we can see because we split by neighborhood first. What if we switch it? What if first we switch by type and then we switch by neighborhood? And I'm also using a different attribute for color coding. Now I'm color coding the variation in price, not just the price. Well, now a different kind of pattern jumps out at us. We can say for a given type, when is there a lot of inconsistency in price between neighborhoods? So for example, if we found a place that was pretty good but not amazing, should we bother to keep looking? Or should we say, oh, they're all probably going to be fairly similar to this one? So that kind of variation is something we are more able to see because within each type, now we can look at the neighborhoods. So the order really matters in terms of the kind of visual patterns. Here's another example. If we have different encodings for the second level regions, right, we don't have to do everything with boxes here. We don't have to be so rectilinear. Here we've got choropleth. So we are looking at these color-coded geographic regions. And then once again, we are able to really think about the geography of where things are different. And we can see, aha, we actually get a better understanding of the geographic patterns of what's happening within London, thanks to seeing these for these 4 different housing types. Okay, now let's think about another family of idioms, which is superimposing layers on top of each other. So by layer, I just mean some set of objects spread out over a whole region of space, like a view, a window. And each of these sets is actually a visually distinguishable group. And so, well, how do we make those things be distinguishable? How many layers could we get away with? How might we distinguish? So for example, we could visually encode with completely different channels. Notice how in my little diagram here, I've got green and I've got black. And so what I'm saying is, you know, everything from one layer is green, everything from another is black, so I can still distinguish them even when they're superimposed. Do we have a small static set of layers, or are we doing something much more dynamic? If it's static, then 2 layers is easy, 3 is maybe possible. If they're dynamic with interaction, there's all kinds of things we could do. So let's look at an example of static visual layering, and a really classic example is a geographic map. And these are so familiar to you, you probably haven't necessarily thought through what's going on here. So we've got a foreground layer, which is these roads. And notice how we've got some distinctions between sort of the foreground roads and the more background roads. But notice that there's that really high luminance contrast between the roads and the backgrounds. And then those background regions like the water and the land, the blue, you know, the light blue and the light green and the tan, those are very desaturated so that we're really able to either attend to those or to those roads. So you can selectively focus your attention. Let's look at another example. With trellis plots, what we're doing is we are actually superimposing within the same frame 2 different years worth of data. So we're not showing the years side by side, the years are on top of each other. Now we are doing a lot of partitioning here. So what's happening with this data set, which is another multi-attribute data set, these are barley yields in different farms in different geographic locations. So first we're splitting by the farming site, then that gives us that the rows are these barley varieties. So we first split by the site, like Waseca versus Crookston versus Morris, and then within those, we are splitting by the variety of barley. Now, one thing that's going on here is we're being smart about what order we do things in. So with this trellis approach proposed by Becker and Cleveland, this idea of first, for each one of these groups, we find the median value, and we order the rows according to that median for the variety, and the views themselves we're ordering by the median of the site. And so we're actually able to see these patterns. And one thing that can really jump out at us is, wow, what's happening in Morris? Look, everywhere else, the blue is on the left and the pink is on the right, roughly. And here's an inversion. Was there possibly a data quality problem? Is this actually what happened? It allows you to notice this disparity and then investigate further. So what are the limits of superimposing, right? Well, we just saw 2 years on top of each other. That was just fine. If we have, say, line charts, surely we could put a few line charts all on top of each other. But if we put hundreds of things on top of each other, it's going to be very, very difficult to see, as we can see in this example on the right. So clearly there's some sort of limit for static superimposing. So like many questions in visualization, people have started to do empirical studies on human subjects to try to decipher, what are some of the design guidelines on this. And one thing they found with superimposing on top of each other versus juxtaposing with side-by-side views, like small multiples, is, well, for one thing, when they studied this, they had to be careful to have the same size for the entire view with the superimposed versus all of the small multiple views. They really wanted to account for the fact that you had fewer pixels available in each of the small multiples. So here we see an example of that. To cut to the chase, what they found was that when you're superimposing for tasks that involve only local judgments, that can go quite far. Once you start needing to do global judgments, it gets to be much easier when you've got the side-by-side juxtaposed views. But what kind of layering can we do if we're dynamic, if we're interactive? And so this is something where instead of just saying statically, I have to make decisions, you can dynamically doing something based on the user selection. So here's an example with 2 different flavors of highlighting the one-hop topological neighborhoods in a graph. And I want to make a distinction between what we can do with this relatively heavyweight motor action of clicking versus this much faster dynamic hovering of moving the mouse. So let's take a look here. So notice how as I move the mouse, it's just briefly showing labels, but I have to click to actually see the edges in this graph. This is a dense enough graph that they're not actually drawing all of the edges at once. They're drawing edges only on clicks. So I'm looking at the relationships between philosophers, seeing what's happening with Levi Strauss and Nietzsche and Kant and Hegel. So I have to click in order to see these highlighted edges. So this is a very extreme form of visual layering. Now, what about another one? This is something where it's just ballistic. As I move the mouse, I can very quickly highlight. And so this is some difference between hovering and clicking, but both of them have this idea of dynamically and interactively having a top layer for something that is related to the selection with the cursor versus the bottom layer, which is not. So we can definitely get, we're not just limited to 1 or 2 or 3 layers. We can have essentially a near infinite number because we're doing stuff dynamically and interactively. So we've now talked quite a bit about these ideas of interactivity with a single view and with faceting the data across multiple views. So we've gotten much of the way through, we've already talked about a lot of the visual encoding techniques, and then we were talking about these 2 more ways of handling complexity.